Hi class, welcome to the first lecture in our remote segment of thermodynamics. So hopefully you remember that the first half of the semester we spent learning about the first law of thermodynamics, which is the conservation of energy. And it states that energy can neither be created nor destroyed, but it can be transformed, right, from one form to another. And we also talked about the mass energy equivalent, and we went through control masses problems, control volume problems, and then we started to move into an integrated systems integration. So we started integrating different components. So now, for the second half of the semester, we are going to add on, and we are going to look at the second law of thermodynamics. And as you have already seen, if you've watched the first two videos that I posted, the second law of thermodynamics tells the directionality of processes, spontaneous processes. So spontaneous processes are those that do not have an external driver and they occur naturally. Then it also introduces the concept of entropy. And entropy, right, is the tendency toward disorder, or it's the degradation of the quality of energy. So useful energy transforming to waste heat, Q, for example. And we're going to spend the next few weeks really looking deeply at the second law and its applications and its implications. So let's get started on this first lecture, introducing the second law of thermodynamics. Now, like I already said, with the second law of thermodynamics, it introduces the directionality for spontaneous processes. And so let's look at the directionality of some processes here. So, for example, we already know this, right? Temperature gradients. So looking at temperature gradients. So in nature, heat is going to flow from higher temperature to lower temperature, right? So high T to low T. Now I'm writing out a lot of these notes by hand to give you time to follow along and write down the notes along with me. I'm also going to post, I'm going to export and post a PDF form of these notes to Moodle. And we can also look at pressure gradients. So the direction of pressure flow, right, is from high to low pressure. And that is also how weather systems move, right, from high pressure to low pressure. There's something in there called the pressure gradient force. And also, we can look at gravity. So gravitational gradients, as far as potential energy is concerned, is from high elevation, so high Z, to low elevation, to lower elevation. And so the initial conditions based on the second law cannot be restored spontaneously. So let's think of a simple example here. Let's just hold up a ball and drop it to the ground. Now, the ball is not going to spontaneously raise itself back up and levitate back to your hand. It's not going to throw itself from the ground back into your hand, right? So that's one example that it's going to, by gravity, go from higher elevation to lower elevation, but the process is not going to reverse itself spontaneously. Someone actually has to expel energy, bend over, pick up the ball, and raise it back up. So that is putting energy into that process. Same thing with, water will flow naturally downhill, but we have to pump it using energy to move it back uphill. Now, also, just adding to this here, looking at the second law, it also shows us the tendency for system to move toward equilibrium with its surroundings. So for one example, so if we have dye, some red dye, and we drop it into water, that dye is going to disperse, and over time, all of the water is going to be red, right? And then the process will stop because it would have achieved equilibrium. The same thing happens along temperature gradients, right? So heat flow ceases once we've achieved thermal equilibrium. And so now, and of course you get stronger winds when you have a sharper pressure gradient, right? When you're going from higher pressure to much lower pressure, right? As there's not a difference in pressure, you're not going to have a wind caused by pressure. So energy and mass balances alone cannot tell us a process is likely to occur or its directionality. We need the second law for this. Okay? Now let's talk about some uses for the second law. So like I've said many times already, the second law predicts the direction of processes. And remember, a process, right, happens between two states. And the second law also establishes the conditions for equilibrium. Third, it determines the theoretical performance of cycles, engines, etc. And we're going to talk more about that in a little bit. And in a couple lectures, we'll get into the theoretical upper limit for cycle performance, for cycle efficiency. Fourth, it evaluates the factors that preclude optimal performance. Fifth, it defines the temperature scale. So remember the absolute temperature scales, the Kelvin and the Rankine scale, right? We just define absolute zero as the temperature at which all molecular motion ceases. Sixth, it develops meanings for evaluating internal energy and enthalpy. Okay, and so remember, enthalpy, we're looking at P delta V. U, we're usually looking at some heat transfer with temperature change. So for there are three statements that describe the second law. So the first is the Clausius statement. And what the Clausius statement says is that it's impossible for heat to spontaneously flow from a cold reservoir, so some cool temperature, to a hotter reservoir, to some warmer temperature. So it does not flow from low temperatures to high temperatures. So that's part one. The second statement that defines the second law of thermodynamics is the Kelvin-Planck statement. And what that says is, it's like, let's consider some thermal reservoir at a constant temperature. And the extensive properties can change, but it's impossible for the system operating in a thermodynamic cycle to deliver net work to the surroundings while receiving heat from a single thermal reservoir. So we're saying that this thermal reservoir, this idealized reservoir, cannot change temperature. So you'd have to have this so typically a reservoir is less sensitive to temperature change the larger and larger it becomes. So just think of a small pond, and say you were discharging warmer water, like just a small amount of warmer water to this small pond. Well, the temperature of the pond is going to increase over time pretty quickly. How about if you tried to do that into the ocean? Well, it's going to take a lot longer to see any kind of noticeable change in temperature to the ocean. It possibly on the order of thousands of years, just by one small input of slightly higher temperature water, for example. So they're idealizing reservoirs, saying, okay, so let's think about a reservoir that is not changing temperature. And remember, we could still have energy transfers without necessarily a change in temperature. Just think about a phase change. Okay. So now let's look at the next piece. So they're saying that it's impossible for a system that's completing a full thermodynamics cycle just to draw heat from the single thermal reservoir to produce some net W, some net work to its surroundings. So remember, work done by the system is positive, work done on the system is negative. Okay? So let's apply the first law to this scenario for a second. So the first law says, well, then the net work done by the system has to equal the heat input. But how would heat flow just from a reservoir at one temperature? Where is it going to go? Where is the temperature gradient? Right? Where is the thermal gradient? And part two from the second law, the implications here is that, well, you can't produce work this way. W cycle is going to be less than or equal to zero. You're either not going to produce any work, or work is going to be done on the system in this case. So now think about this. This is talking about a full cycle. It's not talking about just a system and its surroundings. It's possible for a system to receive heat from one external reservoir and still have some kind of work output, but not for a cycle. So that's very important to keep in mind. And the third portion of our definition here for the second law is, of course, entropy. So entropy always increases in an isolated system. So remember, an isolated system is not interacting with its surroundings. It's not exchanging heat. It's not exchanging mass. It's not exchanging energy at all. It's cut off from its surroundings. So a system left on its own, not interacting with its surroundings, well, entropy is still going to increase in that system. And entropy can be transferred across a boundary. And it usually accompanies Q, because remember, Q is a less useful form of energy. So in thermodynamics, we use the letter S for entropy. So remember, so then of course S dot would be a rate. So this would be some change in entropy for the system over time. And the change in entropy for a system over time is going to be equal to the sum of the entropy transferred across the boundary plus the sum of the entropy produced by the system. And so that brings me to irreversibility of processes. So a system and surroundings cannot be exactly restored to initial states following a process, like I talked about dropping the ball from higher elevation to lower elevation. It's not going to be spontaneously restored to its initial elevation without putting some energy in. You saw in the first video, breaking an egg. Breaking an egg, the egg is not going to spontaneously repair itself and put itself back together. So you cannot restore a system and surroundings to its initial states following a process. So that is irreversibility of processes. And some examples of irreversible processes are heat transferred across some finite change in temperature. Second, unrestrained expansion of gas or liquid to reduce pressure. Okay, so if you have unrestrained expansion, you're not going to get spontaneous compression. Energy needs to be put in, work needs to be done to compress that system back to its initial pressure. Third, spontaneous mixing of matter at different compositions or states, right? As I mentioned before, if you think about diffusion, that happens if you have higher concentration. So stuff moves from higher concentration to lower concentration, right? And it mixes. And it's not, once it's mixed, it's not going to spontaneously separate itself back. Fourth, friction. So that's both sliding and with fluid flow. So you know that if you fall and you scrape your knee on the pavement, on the carpet, you get a burn because of friction. It gets hot. There's actual heat there. Hybrid vehicles, you step on the brake, the friction from that process sends that waste heat, it reuses it, sends it to the engine to recharge it. And so there is waste heat Q. So with friction, that movement, that kinetic energy is being transferred to waste heat. And so since you have a loss of energy there, think about the conservation of energy, you're not going to spontaneously get that energy back in its useful initial form. Fifth, electric currents flow through resistance. Okay, so that's not going to automatically reset itself either. Magnetization or polarization with hysteresis. So hysteresis is so for example, magnets would have a memory of their history. Okay, so they retain information about their past states. So if you just, there's a lag there. It's not going to respond to an input right away. There's a time lag, and so it's not going to be able to reverse itself exactly because of that. Seventh is inelastic deformation. Okay, so any break, things do not automatically repair itself. Any bend, they do not bend themselves back into their initial shape. So no natural process is perfectly reversible, but we can approximate. And some examples of approximations that we use quite a bit in this course are when dealing with, say, gas traveling. Oops, lost my pen, 1 second. So for example, gas traveling through a nozzle or a diffuser. So remember, when we're looking at a nozzle or a diffuser, those are pretty quick processes. And we're not having, if you remember our models, we're not exchanging heat during those processes. So we can approximate that at those as reversible when we're dealing with nozzles or diffusers. Internally reversible, well, that is when all the intensive properties remain unchanged and uniform at each intermediate state of a closed system. So remember, intensive properties like density, specific volume, specific energy. Now looking at returning to Kelvin Planck once again. And so, as we talked about earlier, W cycle is less than or equal to 0. Okay, so that's work done on the system. Applying the second law. And it's going to be less than 0 if we have internal irreversibilities. And it's going to be equal to 0 if we have no internal irreversibilities. So just to return one more second to the Kelvin Planck statement. So if you consider a cycle, a thermodynamic cycle, you can't have just a single reservoir for heat flow to occur, because heat only flows along a temperature gradient. So if you remember that Mould video, the second video that you watched, he had an example of a Stirling engine that he was showing. And from the temperature of his hand, he was holding the base of the piston cylinder, and that base was at a higher temperature than the surface, right? So there was a heat flow to keep the wheel in motion. So that's an example of higher temperature reservoir, so the hot reservoir and the cool reservoir. You can't have a single reservoir and have some kind of work output from a thermodynamic cycle. And we'll go into lots of examples of this next lecture. All right, so let's wrap up with one example problem. And this is number 5.2 from the book. So shown in the figure below is a proposed system that undergoes a cycle while operating between cold and hot reservoirs. The system receives 500 kilojoules from the cold reservoir and discharges 400 kilojoules to the hot reservoir, while delivering net work to its surroundings in the amount of 100 kilojoules. There are no other energy transfers between the system and its surroundings. Evaluate the performance of the cycle, A, using the Clausius statement of the second law, and we'll do part B, looking at the Kelvin Planck statement momentarily. So in order to evaluate this, well, one, you're probably cringing a little bit just looking at this, because you see from heat is flowing from the cool reservoir to the hot reservoir and producing useful work. But you know that with operating a heat pump, for example, which is the same thing, you are forcing heat to move from cool to hot, just like in a refrigerator, that requires W cycle to be negative, right? Some kind of work input to the system in order to make that happen. So let's just add on to this diagram here and expand this example. So looking here, let's say we extend our hot reservoir and let's extend our cool reservoir. Okay, and this 100 kilojoules produced by this cycle is going to go into powering a heat pump then. So let me draw our heat pump. And this is going to be our boundary. And this is a heat pump. Right, and let's just call this then some QC prime. So it doesn't necessarily have to be the same as the other scenario. So remember, this is cold. Then we have QH prime up here. And this is hot. Okay. So let's look closer. So considering this combined cycle, and we're given the given cycle here is going to be driving a heat pump cycle operating between the same two reservoirs. So let's start with an energy balance. So let's say then we have Q hot from our original cycle plus QH prime from our heat pump is equal to QC plus QC prime. Okay, so that means that QH prime is going to equal QC plus QC prime minus QH. So we can attach some numbers to this now. So QH prime is going to equal QC minus QH, so that would be 100, so 500 minus 400 kilojoules is 100 kilojoules, plus QC prime. All right, so in this case, the combined cycle receives energy by heat transfer from cold, okay, so in the amount of 500 kilojoules plus QC prime, and discharges energy by heat transfer to the hot reservoir, okay, going opposite temperature gradient here, okay, so remember you need an energy input from that, which is the major missing component, to the hot reservoir, so 500 kilojoules plus QC prime in equal amounts. So with no other effect, this is in violation. It cannot operate as indicated. And you intuitively could have figured that out just by looking, well, we have the heat flow going from the cool reservoir to the hot reservoir without any energy input. Okay, so part B then is evaluating this system using the Kelvin Planck statement of the second law now. So let's look at this one slightly differently. I'm going to extend the hot reservoir over this way, and I'm going to extend the cool reservoir over here. And I'm going to have a conductor set up here. And actually, I misdrew on the page before. I was actually evaluating this whole piece there as the system. All right, so moving back. So looking at this whole combined system here. All right, and this is our conductor. Okay, so here we would have 500 kilojoules. And here we would have 500 kilojoules. All right, so let's analyze this. So at steady state, a conductor receives 500 kilojoules by heat transfer from the hot reservoir and delivers the same amount of heat, 500 kilojoules, to the cold reservoir. Okay, so this combined system is composed of a cycle. So we have a cycle here, plus two parts that experience no net change in state. Remember, for a process, if we have an energy transfer with no change in temperature, that is going towards a change in state, a phase change. So the combined system undergoes a thermodynamic cycle, which receives a net amount of energy from the hot reservoir, so 100 kilojoules, and produces net work of the same amount. Okay, and so this isn't working, right? So this is going from cold to hot once again, and it's producing positive work. Not going to work with the second law. It's going to violate it. And don't worry, when we return next class, we're going to go through a couple more concrete, less abstract examples applying the second law of thermodynamics. So thanks for joining me, and I will see you next time.